Okay, what you're going to do first is I want you guys on your notes to just number 1 through 7. And what I'm going to ask you to do is on each one, 1 through 7, I'm going to show you this karyotype and I'm going to make an adjustment to it. And I want you to tell me, according to what you can read in the karyotype, is the individual euploidic or are they aneuploidic? If they're euploidic, you just write euploidic and that's it. If they're aneuploidic, you need to tell me if it's monosomy or trisomy and what pair is affected. Is it the trisomy 1, trisomy 13, whatever. And then I need you to tell me if the individual is male or female, according to their chromosomes, okay? So let's do a practice run. Hold on. Why is it not working? There we go. Okay. So is that person euploidic or aneuploidic? Aneuploidic. Do they have monosomy or trisomy? What pair? Okay, so they have trisomy 12. And is this a male or a female? It's a male. All right, good. That's your test run. All right, let's do 7 real ones. Yes, write this down. Yeah, I'll let you know when I'm done tinkering with it. Okay, that's your first one, number 1. Good? Okay, number 2. Wait till I'm done. All right. Number 4, or actually number 3. Done. Number 3. Okay. Number 4. Okay. Number 5. I'll tell you when we're done. Number 6. And finally, number 7. Okay, can you guys remind me again, what do the red chromosomes mean, or where do they come from? Mother. And what are the blue chromosomes? Father. Good. What do you call the phenomenon where the chromosomes that are similar in almost every way pair up with each other? Like you see chromosome number 5 from mom paired up with chromosome number 5 from dad. What do you call that? Homologous. Good. Okay. All right, let's go over them. So, number one. Number one was euploidic and female. Number two was aneuploidic. They had trisomy 13. You're going to learn this one today. It's called Patau syndrome. And they were male. Number three was aneuploidic. They had monosomy 23. That's the sex pair. This is called Turner syndrome. My Aunt Diane has this. Notice I said Aunt Diane. This is female. 1 X chromosome instead of 2. Number 4 is aneuploidic. They had trisomy 21. This is called Down syndrome. And they had a Y chromosome, so that makes them male. Number 5. One second. Okay. Let me sure I'm sharing this with the people watching at home. Number 5 is aneuploidic. You should just be checking your work. They had trisomy 23, that's the sex pair, and that was Klinefelter's. 2 X's and 1 Y. That Y means that it is male. And we'll talk about that today. They inherited 2 X chromosomes and 1 Y. 47 overall. That's going to be male, but there will be some female characteristics because of the 2 X's. Number 6, aneuploidic. Trisomy 23 again. It's the sex pair. This is going to be called Jacob's syndrome. They had 2 Ys. That is male. And then number 7, aneuploidic. Trisomy 23. This was called poly X syndrome. They were all X's, female. Now, as you guys see, there were a lot more trisomy 23s than anything else. You don't have to have a gender to be alive. So in development, if you have an extra sex chromosome or if you're missing a sex chromosome, your odds of survival are much better compared to if you were missing an autosome, which is one of your body chromosomes, pairs 1 through 22. So what I'd like to get to with you all now are chromosomal disorders. We didn't get to that with my afternoon classes. So there's only 3 known aneuploidic chromosomal disorders in which a person actually lives to birth, where they're actually born alive. Now, there is no guarantee that they will make it to their 5th birthday or their 15th birthday or so on, but these are the only ones that have really been recorded where someone is actually born alive. These are going to be autosomal aneuploidies. The first one is trisomy 13. This is where someone has 3 chromosomes in their 13th pair. Now, is your 13th pair an autosomal pair or your sex pair? They're autosomal. They help build your body. That's really important. You really cannot have much damage to your autosomes because you might not have structures properly developed, and that could really be the difference between life and death. This is known as Patau syndrome. I thought I had it written down somewhere. Let me see if I do. It's not. All right, the next one is trisomy 18. This is called Edwards syndrome. Now, if I'm not mistaken, I think back in 2012, there's a guy running for president. His name's not important. And he had to drop out of the race to be the nominee because I believe his daughter had Edwards syndrome, and you likely don't survive past the age of 14. And so he wanted to spend as much time with his daughter as he could because I think she was 11 or 12, so you're getting close. Obviously, there's going to be difficulties and you're going to have special needs, but this is only the second of 3 known conditions where someone can actually survive. And then the last one I'm sure you all have heard of, trisomy 21. What's that? That is Down syndrome. So you all have 22 pairs of autosomal chromosomes. There's only 3 cases or 3 incidences where someone can have an aneuploidic pair and survive. So they're very delicate chromosomes. It's very important to try to keep them as 2 and not have any parts deleted. Now, the sex chromosome disorders have a much greater survivorship. Okay, first one, my Aunt Diane has this. It is called Turner syndrome. This is X naught. That's not an O like the letter O. That's a 0. And in science and math, you also call 0 naught. N-A-U-G-H-T. So that right there is naught, as in there's nothing there. She only has 1 X chromosome, and she should have 2. This happened due to non-disjunction. If I could take you guys back to yesterday, if you look here, here's what happens to my Aunt Diane. I don't know if it happened in her mother or her father, but what I do know for sure is that either in my grandma or my grandpa, one of them had a non-disjunction event. And so as you all see here, this is what you should normally have. The egg cells have 1 chromosome, the sperm cells have 1 chromosome. So just pretend for a moment that the chromosome in the egg cell is an X, and the chromosome in the sperm cell is either an X or a Y. So you got 1 sex chromosome, 1 sex chromosome, 2 sex chromosomes. That's how it should be. Here's one of my Aunt Diane. Right here. Are there any sex chromosomes in that egg? Nada. Which means neither of these are going to have it. So let's just hypothetically say that had this happened to my grandma. My grandpa's sperm cell was fine. It fertilized my grandma's egg cell. My grandpa's sperm cell had a sex chromosome, and because it's my Aunt Diane, it had an X. But my grandma's egg cell did not have an X. So she only has 1 X instead of 2. Yes, Ayla? They can come from both, but as a woman gets older, it's more likely to come from her. Yeah, it's always because of non-disjunction. I take that back. I want to say always. There's always an exception to the rule. Stranger things have happened. But if you go with the rule, it's going to be non-disjunction. Okay, next one. You have Klinefelter syndrome. This is XXY. This is where a person gets 3 sex chromosomes instead of 2. Now, because you see that Y chromosome, it's a male. But there are female characteristics like little to no facial hair growth, underdeveloped muscles, broad hips. Female breastedness in males is called gynecomastia. Underdeveloped genitalia, and which means that the testes are underdeveloped, which means there's no spermatogenesis, which means there is no reproduction. These individuals are typically sterile. By the way, my aunt is sterile because another condition of Turner syndrome is underdeveloped reproductive organs. All right, next one is going to be Jacob's syndrome. This is XYY. What parent would definitely, undoubtedly, 100% be the reasoning behind this condition? Mom or dad?
Yeah.
Why dad, Jet?
Because that one carries the Y.
Because only your father has a Y chromosome. And if you inherited 2 Y chromosomes, that means that something happened within your father. Mom would be off the hook on this one. Okay, next. Is going to be Swire Syndrome. Did I talk to you guys about the SRY gene yesterday? I believe I did, didn't I? Yeah, the SRY gene is what really makes you a male, or it helps you develop as a male. Swire Syndrome is XY female. Here's how this happens. The SRY gene is either inactive or absent. It might have been deleted. So if you were to take a karyotype of someone and you looked at their chromosomes, they are XY, but they look like a girl. They even have female external genitalia. The SRY gene is what causes a person to develop as a male. And if they don't have the SRY gene, they're going to develop as a female. Well, this person has a Y chromosome, but they're not going to develop as a male because the SRY gene is gone for some reason. Yes, Ayla?
Are they fertile if they do develop inversion?
Nope.
So are all these should be just...
Yeah. All right, next one is the opposite of Swire syndrome. This is De La Chapelle syndrome. This is going to mean XX male. And based on what you guys read in Swire syndrome, how do you think this happened? What do you think? What must be on one of the X chromosomes? Yeah. So apparently during meiosis within dad, the SRY gene jumped off of his Y chromosome and onto an X chromosome, and he passed on the X chromosome. So, you know, if I look at Lauren has an X chromosome from mom and X chromosome from dad. Well, let's say that the X chromosome from dad, and all you girls, let's just say that the SRY gene that your dad has jumped ship and it translocated onto the X chromosome, which he passed on to his future daughter. That means his future daughter will have an SRY gene. So genetically she, but phenotypically, you know, how you look, you're going to develop kind of like a boy. So this is where the SRY gene translocates. That means it changes location. Trans means change. Oops, spelled that wrong. Translocates from a Y chromosome to an X. And then the last one, we have poly X syndrome. This is where females can be 3 X's or sometimes even 4. So they can have 47 or even 48. It has been documented. It has happened. So as you all can see, these people are alive. They can be adults. They can reach adulthood. It is much more likely to survive a condition in your sex chromosomes than it is your autosomes. Yes, Ayla?
For like the XXXX, how does that work, like, for genetics?
We're going to get to X chromosomes today. Hopefully your question will be answered in a little bit. All right. Now, to switch gears here, let's actually go to that next. Let's talk about the X chromosome. So, what are the sex chromosomes of the ladies? Human ladies, that is. XX, and the human males? XY. I say that because not every species on Earth is X and Y. Roosters are WW, and hens are ZW. And I'm also pretty sure, let me look this up, a platypus has like 6 or 7 sex chromosomes. They're the freakiest things. Did you know that they just found out a platypus actually glows in the dark when exposed to UV light? I mean, think about this. A platypus is a monotreme. It's a mammal that lays eggs. That's 1. It has a bill of a duck. 2. It has a body of an otter. 3. I'm counting up the weird things about it. It's venomous. It has like snake fangs on its hind legs. The males are venomous. That's 4 things. Number 5. It glows in the freaking dark. Okay, Australia's weird. All right, let's see here. How many sex chromosomes does a platypus have? 10. Jeez. They have 10 sex chromosomes? What are they? Hold on. What are the sex chromosomes of a platypus? A platypus has 5 X's and 5 Y's. Whatever. Cool. Okay. Now, guys, no matter what sex chromosome do we always inherit from mom? Mom has 2 X chromosomes, so we only receive 1 from each parent. So what do we always inherit from mom? Shane, you have a pass, don't forget it. So we always inherit an X chromosome from mother. That's all she has. That's going to really help you when we get to genetics after the break. You can't pass on something that you do not have. I cannot pass on the brown eye gene. I don't have it. It's non-existent in my person. So if I have kids, if they're brown eyes, it's not going to be because of me. You can't pass on what you don't have. And you really need to just keep that in mind. Very simple logic. Now, what the father determines your gender. If you receive an X chromosome, you're going to be a baby girl. If you're going to receive his Y chromosome, you're going to be a bouncing baby boy. Father determines your gender. Where did your father get his X chromosome from? His mother. Do any of you look similar to your dad's mother? Sometimes that is the case because basically your dad is just a vessel between your grandma to you. Now, here's the question I would like to answer for all of you. Okay, females have 2 X chromosomes. Males have 1. So here's our question. Do females produce twice the amount of gene product from the X chromosome than males. So all the ladies have 2 X chromosomes, all the males have 1. Do girls make twice as much product that the X chromosomes are responsible for? No, you do not. The answer is no. I will tell you why momentarily. Males and females produce an equal amount of X chromosome product. Why? Here's why. Because during in utero development, this means while your mother is pregnant with you, ladies, during in utero development, one of the 2 X chromosomes shuts down. So ladies, you have about 100 trillion cells in your body. Every one of those cells has all your chromosomes, except your eggs. That means every one of your cells has your sex chromosomes, every one of them. One of the sex chromosomes is turned off. This shut down X chromosome is called a Barbody. It's named after the scientist that discovered it. So if I took a bone cell, brain cell, heart cell, liver cell, ladies, I would find all of your chromosomes, including your 2 sex chromosomes. But only one of your sex chromosomes is actually turned on. It's active. So you're on a level playing field with us 1Xers. We only have 1X. You have to stay on a level playing field with us because males and females have to reproduce. They need each other. We don't want the females producing more product, which would put us at a disadvantage, and it might affect compatibility between males and females. So here's how this happens. And I want to answer another question that you may not have thought of, but I'm going to put this question in your head. So let's say during pregnancy, you got 1, 2, 3, 4, 5, 6, 7, 8, 9. During pregnancy, as soon as you guys are a zygote, dad's sperm fertilized mom's egg, girls, you have 2 X chromosomes and they're active. They're active during the 1st month, the 2nd month, 3rd month, the 4th month, the 5th month. And around here, we'll say 7th month. We'll say 6th month. Let's keep it fair. Around the 6th month, let me finish this. Watch this. One of them just kind of shuts down. It's there. Let's make no mistake. It is there. It's just not turned on. Some of you have a car in the parking lot right now. It's there. It's just not turned on. And some of you have no car at all. There is a difference between something being there and not being active and something not existing. So I want to share with you a question I remember asking my genetics professor in college. I went to him after lecture and I said, Professor, I have an aunt who has Turner syndrome. Why is it that my aunt has all these abnormalities because of her syndrome, but all the girls in here have a shutdown X? What is the difference between having a shutdown X and having no X at all? And he said, what I just told you. During development inside of our mothers, both X's are active up to a point. You need both X's during your development. My aunt, who's like this, only had 1X right off the bat. So all the girls in here, you had 2 X's active during 1st, 2nd, 3rd, 4th, 5th, 6th month. My aunt, as soon as she was a zygote, was already missing a chromosome. And so she did not have that benefit of 2 X chromosomes working together to help develop her body. And that's the answer. Are there any questions about that? The difference between having 2 X chromosomes, one being shut down versus not having a second chromosome at all? All right. Okay. So something else I want to kind of go on a little tangent with, we have plenty of time for this, is there are traits on the X chromosome that have nothing to do with gender. Someone asked me yesterday, I think from 4th period, they said, okay, Turner syndrome is where you have one X, no second X. Can someone survive with just a Y? Like they have all their autosomes, they're just missing an X, and they have a Y. The answer is no. The Y chromosome is very, very, very limited in how much information it has. It does not have enough information to complete a person. And so if someone was developing with only a Y, they likely will not be born alive. It will likely be a stillbirth, a miscarriage. Because the X chromosome is responsible for more than just sex characteristics. So the X chromosome carries traits that have nothing to do with gender characteristics. One of which is red and green color receptors. Humans have 3 color receptors in our eyes. We have blue, we have green, and we have red. If you can see blue, you're fine. This is carried on an autosome. I'm not sure which one. I think it might be the 17th pair that just sticks in my head for some reason. I may very well be wrong. So I'll just put autosome. But these 2 are carried on the X chromosome. The ability to see red and green has nothing to do with being a boy or a girl. This is just an example that the X chromosome carries non-sex traits. Another one is going to be clotting factor. When you cut yourself open, you eventually stop bleeding if it's not a huge wound. Well, people who are hemophiliacs have a recessive trait on the X chromosome. So in this one, I spelled that wrong. Hemophiliacs cannot clot easily. This is due to a recessive trait in the X chromosomes. Okay, so before we get to the end of this lecture, I want to give you guys a little preview of what you're going to see after break. And I want to ask anyone in here, is anyone in here colorblind or know someone who's colorblind? Hold on a second. Are you color? Oh, yeah, we talked about you. Anybody else besides? No? Besides Andrew? No? Okay. No one knows someone who's colorblind? You do, Duncan? It's not the kid to your right, is it? Is it a male? All right. I'll tell you why it's more common in males and females. So first period, I had 2 girls who both said that their father is colorblind. So let's play with that for a second, okay? Check this out. So this is a female, right? This is a male. Easy. But something we're going to do after break is sex-linked traits. Let's say if this trait has a dominant allele represented by the capital H. This means you have normal vision. And let's say you have a recessive trait, which is represented by a lowercase letter. This means you are red-green colorblind. People who are red-green colorblind mostly only see grays. I had a student several years ago. His brother was colorblind. He says his mom had to help him dress in the morning until he finally got the hang of it. Make sure he didn't clash. Christmas can be very gray for some people with extreme cases. So let's say that we have these 2 girls in my class, first period. This is both of them. The girls can see color because they have the dominant trait. but they also carry the recessive trait, which means that these two girls are carriers. If you remember from freshman bio, we call this heterozygous. Hetero means different. Let's say that they end up with Mr. Perfect. Mr. Perfect over here only has one X chromosome. And so when it comes to X-linked traits, males either have them or they don't. Males cannot be a carrier for a sex-linked trait. That's what these are called, sex-linked traits. Males are either normal or affected. There is no carrier state. So this male is normal. So let's say these two girls, they end up with this guy. They want to have a family with him. And so here we go. Here's the female. Here's the male. Okay? Each box represents 25%. They have a 25% chance of having a child that will be a girl and completely unaffected. There's no trace of the recessive trait. They have a 25% chance of having a daughter who is a carrier. They have a 25% chance of having a son who is normal. And they have a 25% chance of having a son who is colorblind. And so I told the girls, if you have a boy and they're colorblind, it's your fault. Because more often than not, the boy, actually every time, I shouldn't say more often than not, every time a male is colorblind, they inherited that from their mother. Because what does the male inherit from the father? The Y. There's nothing carried on the Y that's of great significance here. It's the X that it has the trait. And so I want to just ask you guys a few questions because this could be the big difference between getting it right and getting it wrong. So listen carefully to the questions that I'm asking, okay? Listen. What percent of, and this is all statistical probability, what percent of their children will be colorblind? 25%, okay? Good. Listen to my words. What percent of their sons will be colorblind? You see the difference here? The answer is 50%. Because if I say what percent of their children, I'm talking about this entire pedigree, or excuse me, Punnett square. But when I say what percent of their sons, we're not even talking about the daughters anymore, just the sons. And so it would be 50%. That's going to be really important to interpret those little teeny tiny differences when you're asked questions. And you will be asked questions like that. You will be asked what percent of the daughters, what percent of the sons, what percent of the entire offspring possibility. There are differences when you're asked that. Now, in my entire life, I've only met one girl. It was a student of mine 6 years ago who was colorblind. I've only met one female ever. Have any of you ever met a female who was colorblind? Super rare. Here's how that would have to happen. Mom would have to at least be a carrier and dad would have to be colorblind. So if you look at that, let's set that up. So here's mom. She's a carrier. Here's dad. What is that daughter? She's a carrier. What is that daughter? She's colorblind. What is that son? Normal. What is this son? Now, pay attention. This is mom's mutated chromosome. Mom and mom. Here's mom's normal chromosome. Right there and right there. The point I'm making to all of you is that the boys inherit that X chromosome from mom. So any boy that has a little stint of colorblindness inherited from mother. Thanks, mom. Now I was sharing this. I was sharing this with you yesterday with Andrew. Check this out. I haven't done this with any other class, but why not? Several years ago, the NFL started a color rush campaign. If you like to watch the games, you ever notice when the Buccaneers would wear all red, like red jerseys, red uniforms? That was their whole color rush thing, where every team is monochromatic. Like the Miami Dolphins wore all teal, or the Chicago Bears wore all blue. Well, the first game that they did was the New York Jets versus the Buffalo Bills. And they had the New York Jets were all green with white helmets, and they had the Buffalo Bills were all red with white helmets. Yeah, there were problems. So I want to show you this. Color Rush, Bills versus Jets. So this is what it looked like to people who have no issue with colorblindness. See if I can find a good image. You see the title of that story. Well, you guys can see for yourself. I can't make the image any bigger. So here's what people at home would see. And then here's what colorblind people saw. Basically, they saw a gray field with 22 guys wearing gray uniforms, and they couldn't tell the difference. And so the NFL got a tremendous amount of calls the next day, like, I can't see anything. I don't know who has the ball. I don't know who's who. And so they're like, oh, we didn't think of that. 8% of the population is colorblind. Oops. So they stopped doing that. So, or they didn't stop Color Rush, but they said, all right, we'll make one team wear colors. We'll make the other team wear white. So you can't tell the difference. But it was kind of a mess. So let me show you this. This is what it looked like to the colorblind person. I mean, tell me, who's the Bills and who's the Jets? Who's wearing gray and who's wearing green and who's wearing red? You can't tell. This is what it looks like to a colorblind person. All right. So that was definitely a learning experience for the NFL. Okay. Let's finish off today's class with some chromosomal additions and deletion mutations. Okay, I only have about 4 minutes, so I'm going to have to hustle through this, guys. We first have a duplication mutation, where you have a part of a chromosome is replicated on the same chromosome. So here's a normal chromosome. Let's say it read A, B, C, D. That would be normal. Here's the mutation. A, B, C, D, C, D. It duplicated itself. That's a mutation. The next one is called an inversion mutation. This one's pretty easy. A part of a chromosome is inverted 180 degrees. Basically flip-flops. Are these what? They can be, yeah, because you don't have the gene in the right spot. For when the gene has to be expressed, it's not in the correct place. So normal would be A, B, C, D. Here's mutation, A, C, B, D. Flip-flop. Gene C and gene B flop-flipped. We have translocation. A segment from two neighboring chromosomes switch positions. Trans means change and location is where you are, so they're changing where they are. So here's normal. You got A, B, C, D, E, F, G, H. Those are 2 chromosomes. Here's the mutation. A, B, G, H, E, F, C, D. See how that works? Translocated. All right, we'll have to stop there. There were a couple other mutations, but we can get to them at another time. A deletion and an addition, or a substitution. We'll talk about those later. We'll make sure we get them. All right, that's all.